Hello and welcome to another episode of Scala Space Podcast. Today, my guest is Mateusz Kubuszok, long-term Scala engineer, consultant, and the co-author of Chimney data transformation library. This episode is a bit special for me, and I'm very excited to have Mateusz here. And I'm excited for completely nerdy reasons. And that is because the topic we are going to talk about is quite technical. It's probably not the most approachable thing to discuss, and probably not something that is very easy to comprehend for newcomers, but we'll do our best to go through that in a way that explains everything very precisely. So I wanted to start, Mateusz. When we started talking about this, you told me that you are kind of apprehensive that you might make many people angry in the Scala community because, as we agreed, you basically your message is that well, hey, Scala community, you were basically holding it wrong the whole time. So let's dive into this and let's tell our audience, why do you think this way? So my first question to you would be to introduce the concept of typeclass derivation in general. Could you tell us what do you think it is and define it for us?
Okay, so hello everyone. So the typeclass derivation is something that probably most of you were using if you were using Scala, unless you were struggling really, really hard to avoid it. It's basically a way of generating some code that does things for you. The most common examples, probably the only examples you think really, really hard about is generating codecs in such a way that if they are possible to be generated, you simply get your code compiling. If it's impossible to generate them, your code will fail to compile. And this way, hopefully, you could see that, okay, my code's compiled, so those JSONs or conversions from one type to another or pretty prints, things like that would work out of the box. No need to test them. Of course, you need to test them, but you can think you don't need to test them because the compiler itself is a proof of everything. And basically, the idea is that we in Scala try to avoid runtime reflection because you could obviously use runtime reflection for all of these things. You could just say, okay, let this magical piece of code take your type and take your data and figure out the way how to, let's say, encode a string into JSON or decode JSON into data, things like that, and it would work. Yeah. But obviously, the tiny little issue is that if it doesn't work, then you only learn about it after you write tests, or if you're move fast and break things kind of person once you deploy it to production. So some of us prefer to learn ahead of time because it's less stressful to fix things on your computer than to fix things once your customers see it. So we prefer to use this thing called compile time reflection, which basically means that the compiler would somehow take a look at your code and your data. Most of the time by data, we mean case classes and sealed threads or enums, and then somehow use their structure to generate the implementation out of them. And that's basically all that there is to the typeclass and typeclass derivation. Typeclass is just an interface. You write a trait, define some methods that you want to use later. This trait would be like type parametric because you want to have a separate implementation for, I don't know, string, an int, and my case class, my address, my user, whatever. You want to distinct the implementation by the type parameter that you applied there, and then you want to shove it onto the compiler to pick up all of this implementation and provide to where you need them. And that's basically the big idea. The rest is like a bunch of implementation details that are very, very leaky, as you might learn if you are Scala developer for a long time. So this is something that we'll be discussing today, how much they are leaking.
Okay, so just to quickly add, you might have already used generic derivation or typeless derivation if you used libraries like Cersei or JSON or Scala or upickle, because they do use typeless derivation to create codecs. So basically, pieces of code that handle the composed data type for which you derive the type class, that know, given that they know the static structure of the data, how to encode and decode that into some form of data or even SQL query. Because Doobie library for SQL also uses type classes and also derives them. Okay, so Mateusz, let's quickly talk about how does type class derivation work? What has to happen for a type class to be derived by the compiler?
So like 99% of time, if you want to use typeless derivation, let me share a screen. We're only considering like 3 use cases. First one, we have a case class. Second one, we have a sealed trait or sealed abstract class or Scala-free enum. Let's say as far as compiler cares, they're like, and as far as the derivation cares, it's the same thing, like some enumeration. And the third use case is some built-in types that we already provided, or to be specific, that the library author provided. And then the idea is that you take a look inside the compiler, how your case class or how your sealed trait looks like. So what are the, we are talking about case class, what are the fields of this case class and what are the types of each of those fields? And then we're assuming, that's the basic assumption, that if I have implementation of this trait, of this type class, for every single of those fields in the case class, then I know, the library author, know some way how I can combine them together to make the implementation for a whole case class. And it's such a generic way that I can tell compiler, okay, if you see case class with fields, name of the field, type of the field, name of the field, type of the field, smash them together and give me the result as a implementation for a whole case class. Same for the sealed traits or enums or sealed abstract classes. Take a look at each of the subtypes. Give me implementation for each of those subtypes. I will tell you how to combine them together by dispatching things into the subtype with some sort of way or whatever. And you will give me the implementation for this whole enum type or the whole sealed trait. And that's basically it. That's what all of those libraries are doing. They are defining some like built-ins, like implementation for strings, ints, doubles, whatever they want to support out of the box. They're telling the compiler, okay, if you will see case class, I am telling you how to combine those fields together. If you see sealed traits, I'm telling you how to combine those subtypes together. And compiler does precisely that. Gives you the implementation of this interface, which basically combines the smaller behaviors into the bigger behavior.
Okay, Mateusz, so historically, what kind of approaches to generic derivation we had in Scala? Because this is a longer story. We have 2 different versions of the language currently, Scala 2 and Scala 3, and things have changed. Let's have an overview on a historical perspective.
So it all became possible to do the things we are doing when Eugene Burmeko defined the first macro implementation for Scala. Before that, you could have those implementation. You have implicits that you could implement them, and this is the way the compiler provides some stuff to you. But there wasn't generic way for making it work for every single case class, every single subtype. You basically had to write every single implementation manually. So this whole implicit thing was only about providing that you already implemented yourself. It's kind of useful, but not super useful. Then macros became a thing, and one of the use cases that you could use macros for was to define basically this what we are talking about right here on this picture, generating implementation for case classes and seal traits. But macros are not easy to do. So people wanted to avoid macros at all costs. And then Miles Sabin came up with an idea how we could avoid macros altogether by basically translating this format we have, our case class, into something like something similar to a tuple in Scala 3, when you can start with empty tuple and then prepend field, prepend field, prepend field, prepend field. This way, build up tuples as if they were lists. And his idea was, I will write you a macro which will translate your case class into such a build-up tuple, and then you could use like basically recursion to build up implementation for such a tuple, and also convert to and from this generic representation. And this way, basically implement some generic support for every single case class. And similarly, the same thing for those seal traits. He also give you something like an either, but either of not two types, but something like no type, or my type 1, or my type 2, or my type 3, and then you can have this big buildable either type. So with those two things, people were able to build those libraries based on typeclass derivation, like Cersei. Cersei is like the biggest success of this approach, and based on findings how this library was developed, you could also see how things were described to users as a sort of manual of this sort of derivation way. And typeclass astronaut guide to shapeless, if I remember the title correctly. Basically, this manual is taking the CSA approach and turns it into like a manual for the user how you can implement derivation for your own stuff in the same way. So that was the first approach that actually took off, because it didn't require users to learn compiler internals. But it has some issues when it comes to performance, and both runtime performance and compile time performance. So after a while, people didn't want to give up on their typeclass derivation, because they found it extremely useful to be able to make sure in their compilation that their code is working, while they didn't want to write macros themselves. So they want to still use this approach, but maybe make it work slightly better. Also, like the error messages are something abysmal, because usually you only see implicit and found, and that's all your error messages if something goes wrong. So then a third approach appeared, which was Magnolia. And Magnolia once again used macros to give users some sort of interface. And it embraces the most common use case, basically that your interface have only one type parameter. So you can have a case class. You can assume that if you have, let's say, encoder of my user, and you have name of the user, surname of the user, they are strings. So that then it would try to find out type class of strings for the name, type class for strings for the surname, etc. And give you this interface when you would combine those stuff, not like a with bunch of implicits doing this recursion translation back and forth, but you just receiving a single value representing the whole case class, all of its fields, and you can use it to combine things in the runtime. And it appeared that this was both faster for compilation, and oftentimes also faster in the runtime, as some of the benchmarks were showing. And so a lot of people migrated from Shapeless to Magnolia when they cured. Thing is, it was quite a long time ago, and for a while nobody did any sort of benchmarks. And in the meantime, while subbing out of the Shapeless, were working really, really hard to optimize those Shapeless derivations. And his work finally landed in some of those milestone versions of Scala 2.13. So while a lot of people develop some intuitions how implicit works, what is slow, what is fast, those intuitions don't necessarily hold as much if you're trying to use Scala 2.13, because things went a lot better, and the differences between like Shapeless, Magnolia, as far as I could tell, they are much less prominent. Basically, those three approaches are what dominates the Scala landscape today. On Scala 3, some of the things that Shapeless provided, this way of introspecting the case class, letting you learn about what are the names of each of the field, what are the types of each of the field of the case class, what are the subtypes of a seal trait, what are the names of the side types. Those things are built in, and those built-ins are called mirrors, and also there are like inline defs, which allows you to work with stuff also like without relying on this super nested bunch of implicits. There are implicits still, but not as much as with Shapeless. And then with those inline defs, you could use mirrors to build on top of it. And also there's Magnolia on Scala 3, which has very similar API to Magnolia on Scala 2, but not identical. So, well, basically you can treat mirrors as some sort of Shapeless counterpart on Scala 3. There is Shapeless on Scala 3, but as far as I care, as a developer of a library, if I had use cases for Shapeless on Scala 2, on Scala 3, they usually disappear. There are some things that Shapeless on Scala 3 still provides, but I never need to use it. So for me, mirrors completely replace Shapeless. Magnolia, as far as I can tell, it offers much better API than Shapeless if you are a library developer, but while on Scala 2 it offers you some improvements, on Scala 3 it comes with a cost, unfortunately.
Okay, so Magnolia by John Pretty, I think it did something really interesting when you think about it, because I did use Magnolia for some of the customer-oriented internal stuff at VirtualSub, and it seems that the whole interface is that you just have to implement two methods that won't be called in runtime. I mean, to some degree, but they will be, but they are used by the macro itself. So there's just a macro wrapper that uses your code to construct stuff that is then used as the instance of the type class that you wanted to derive. It's quite ingenious, if you ask me. But on the other hand, you lost a lot of type information with that. So happy mistakes were made. Excuse me. I wanted to ask, how did you get into the situation where you have all of this knowledge in your head? What developments on your part left you with all this understanding and experience?
So I never intended to become an expert in this kind of stuff. It was an unfortunate accident. Basically, over 7 years ago, I tried to build my own startup, which failed, which is a common history among a lot of us. But one of the stuff I had to do in the startup was building a backend. And in this backend, really try to separate the types used to represent, front-end types, all these JSON case classes from the code that was handling like the domain code, and from the events that we were storing somewhere, and then making projections from those events to stuff. We wanted to have separate representations we want to interact with. At the time, Sleek was the thing. It was before Doobie became such such a big hit. So also like separate types for Slick. And it was a real pain to convert back and forth all these things when I had to write it manually. It was so super repetitive with mapping fields, and if I tried to use something like new types, not the new type Scala library. At the time, it was most usually either type tags or like case class extending an eval or things like that. But still, you have to wrap, and it was such a pain if you really wanted to have a safe code, make it easy to maintain, but convert between all those presentations. So at one point, me and my roommate Piotr Krzemiński started to developing like this fun library for fun, and we started doing it with Shapeless, and it was doing the things that I wanted, like ideally, like converting from my case class to another case class. Whether the fields change position didn't matter because we only looked at the names of those fields, so we could reshuffle the orders of those fields, and everything was still working. If you dropped some field in the outcome, it was still working out of the box. And if there was some new fields or something got renamed, there was an API which allowed you to basically tell the compiler, okay, I want to convert this from that into this, but this field will be renamed, and this field is not existing on the input, so use this value. And we did all of that with Shapeless, and it was working. But in one of the projects I started working later on because startup didn't play out, and I have to, put a food on the table to, survive. So I started working for other people, and they were also use cases for like Chimney, the library that I mentioned, and especially in some sort of like ETL transformations. But the problem was that with Shapeless, when I wrote some transformation, it was just 2 case classes, and that's something I even tried to export them to a separate module. So if I wanted to generate this conversion between those 2 case classes, it would be just only this module, and everything else would cut the result, because the single file, which had less than 50 lines of code, was compiling for over 2 minutes. It was basically killing our performance, and it was like, okay, it's completely ridiculous. I would have to completely give up on this approach or do something about it. And then I started talking to Piotr, and we came to the conclusion that, okay, there is one way to make this derivation faster. We have to get rid of Shapeless and do this inside macros. I don't remember if Magnolia at the time was already a trend, but even if it was, so Magnolia have this nice little assumption that you have a single type parameter, and if you're writing basically a converter from one type to another, you already have 2 type parameters, so whatever Magnolia provides isn't going to work,
sure,
for various reasons. Yeah, so then we wrote it into macros. And ever since, it was a long story of learning every once in a while that we didn't cover some use case, so we need to add it. Then we, for a while, added support for Scala 2.11 because we started with Scala 2.12. Then we dropped 2.11, then we added 2.13, which we are supporting to this day. And over the years, we got so many requests about new features or use case to handle, or some corner cases that you write your code, you think, okay, it's going to work, and it's not going to working because, well, macros are not very good at handle, corner cases. Either you know about them and handle them yourself, or you get some nasty compilation errors, like exceptions from macros. But after a while, and a lot of tests, we got to the point that the library is really, really stable. And also we had to come up with a lot of ideas, like how to write the macros. Basically, my biggest lesson was that if your macro is bigger than like 1 file, even like a huge file, it might be a nice idea to start treating your program like every other program you're writing in your everyday job. So create a types for everything. Like you don't pass around row strings or row untyped trees. write yourself some enum for errors. If you can have multiple errors, store them in the list or non-empty list or whatever. Have some either it works, either of it works or it doesn't, and that helps you a lot. And then try to separate all of those methods into some meaningful domain like uh, representations. Now I am working with case classes. Now I am working with sealed threads. Now I'm working with whatever. Now that I'm handling something like that, and the code gets much more readable. And also at some point you will also start thinking, okay, I have errors. I have aggregating errors. So if I can also handle things like recursively, because then I don't have to allocate a new type class for something that I don't really care about. Like most of the time, when you have a case class, inside you have a case class, inside you have a case class, etc., and you try to encode or decode, the top one. You don't care about the implementations for intermediate values as long as they give everything is giving you the right results.
So basically, you became enterprise macro developer.
Yes, it became enterprise macro development, and especially our movement to support Scala free. Like it was like, okay, so we have to refactor things again because the code we have right now it's really nice, but we're really tied to this low-level macro representation. So basically, we had to move away from it, make macros an implementation detail. Otherwise, we would have to do what much like many others libraries did, which is like either you have a version 2.0 for Scala 2 and then version 3.0 for Scala 3, and you have two completely different versionings, or you have things like, okay, we have a common API for Scala 2 and Scala 3, but the macros, they are completely separate, written from scratch, and everything which makes macros for Scala 2 and macros for Scala 3 behave in more or less the same way is a bunch of unit tests. But of course, we are not writing unit tests, because why should we write unit tests for CodeGen? CodeGen is supposed to work if it compiles. So if it compiles, it should be the same behavior on Scala 2 and Scala 3. And then you might learn that it's not always the case. So we early on decided that if you want to support two versions of Scala, and if you want the behavior to be on parity, if I am telling you that it's on Scala 2 it works this way, on Scala 3 it should work exactly the same way. So documentation wouldn't need to have those tiny little notes.
Yeah, exceptions.
But if you're using actually Scala 3, that's not really true. So we didn't want any sort of that crap. So we came to the conclusion that the only way to make sure that Scala 2 and Scala 3 have the same behavior is they have the same implementation, which means that we have to share the code between Scala 2 and Scala 3, which means that we had to make the macros an implementation detail. So that was a huge rewrite that let us sort a lot of things out, and this way we were also able to fix a lot of bugs, implement and later on add a lot of new features, because this refactor code was much easier to work with, and it was much easier for us to add new stuff. But well, it was a pain.
Okay, so correct me if I'm wrong, but we are actually getting in this history to the thing that you have found, the thing that is the topic of this podcast, which is the new approach to handle derivation that you have discovered works in a better way. It's faster in both runtime and compile time. So before we jump into how that works, I think it would be beneficial for our audience to have a better understanding of the differences of how the guts of those derivation algorithms work. I know that you have those nice slides that you had on your presentation on last two conferences, I think. Could we briefly go through how those algorithms work so that we can see where the difference is, okay?
Sure. So, okay, let's start with the slide. Like what it describes is usually how Circe and all of the libraries based on it are approaching things. There are some slight differences when we start talking about the approach that I am talking, but this is like a starting point. So if we looked for a concrete example, how CRC would derive things for, let's say, encoder. Let's say we have a case class, it stores address, and then we have a user which has some name and also an address. And then we try to summon the encoder for the user. Usually, like, getting the implicit is how the APIs for all of these libraries are working, and this implicit has the implementation. So if we have a CRC and we are deciding to using the thing called automatic derivation, more on that later, the way it works is more or less this. We are summoning the encoder for the user. So the compiler takes a look, okay, do we have this encoder of a user defined somewhere explicitly? Maybe you have this in your scope directly, maybe you have it inside some of the traits that you mixed into the trait that the class you are currently in. Maybe is inside the companion object, because companion objects are always looked for this kind of stuff. Maybe it's imported by some of the imports that you written on the top of the file. Anyway, compiler takes a look. Have you or someone else defined this in anything that's in the scope that you currently see? If there is, it's going to use it. But if it will not find this user, then it will have to dig deeper. And then it will find out that inside some of the stuff that inside one of the imports, we defined this generic idea, which should be used as a fallback. That's very important. You always want to trigger this derivation behavior in automatic derivation as a fallback if there is nothing provided. Otherwise, it would break your stuff if you want to. Okay, I'm pointing you need to use this implicit, and compiler would be like, not really. I'm gonna
create a new one.
Give a new one. So it's very important that this automatic derivation stuff is always working as a fallback if there is no provided by you or your colleagues or whatever. So this stuff is looking on the user, looks whether it's case class or CL trait. Let's assume that we are only looking at case class example. So if it's not a case class, then it's like, okay, I cannot do anything. I cannot help you, and we are done. So your tour to get your request for obtaining this encoder for user ended in failure. Sorry. But if this typeclass derivations things is saying, okay, this is a case class. Okay, this case class has a name of type string and address of type address. Okay, so I have to find implicits for each of those fields. So do we have an encoder for string? And CRC, as a matter of fact, does have it defined inside a companion object, so it will be found and it will be used. Okay, nice. Okay, so now we have to look at another field, address. Do we have an encoder for address? And nobody defined such an encoder, so as a fallback, we take a look, is address a case class? If it wouldn't be a case class, then again, we would fail. And again, our quest for getting this implementation finished, with a huge failure. But we see that, okay, address is a case class. It has one field value of type string. Okay, so if I can find this encoder for string, I will use it. Of course, it finds it because it's defined as the encoder companion object in CSA. Okay, so since all of these type classes were found, so then the typeclass derivation defined for CRC used its logic that the authors of the CRC defined to combine those smaller implementations into the whole encoder of the address. Then user sees, okay, I have encoder for string and I have now encoder for the address, so I can combine it into encoder for user. Okay, this is the implementation. Please, my dear user, you can use it. And that's basically the idea of this automatic derivation. If you have automatic derivation, then one thing is that it always works as a fallback. And the second thing is that if you don't have definitions for those intermediate types, it works recursively. So you will generate those implementations as in, on bytecode you could see, new classes extending those stuff, which you would have to instantiate in the runtime, etc. But all those intermediate types will be created and combined together.
Let's define what recursive means in this context, because there's this arrow between, I think, is there existing encoder address, right? So if it's not found, if there is no implicit in the scope, what actually happens is that the macro is retriggered. So it's triggered again because it's a fallback, like you mentioned. And then you have, during the compile time, you have this process in which the tree is traversed, and each step downward is also, if it's a case class or a sealed trait, it also means that it will trigger an expansion of macro. So it's kind of compiler happy in this regard. I think you also missed the fact that it doesn't have to be a case class, right? I think any.
Yeah. I didn't want to make it too big,
so
because you always have to,
sure.
Is it a use case, or is it a sealed trait, or is it something else? Like, so I made this, simplification when we are always considering, is it built in, or is it a case class, or is it provided, because it's already a lot of those flowcharts.
So basically, it's the same process for sealed traits or sealed abstract classes.
Exactly.
But just with children, so subtypes. Yeah. Okay, cool. So that's the auto derivation, and it's a common knowledge by now, I think, in Scala community, that auto wasn't probably the best idea. Could you explain why it was shunned upon? People started dropping the use of auto.
So when you're creating a new implementation, like here, it's like a new encoder for user. If you don't see an existing encoder for user, you have to derive it. And this means that if you have to use the encoder for user in one file, and then in another file, and then in another file, and then in another file, every single time you would trigger this process of, is there a user? No, create it, use it, this step, etc. So you have to rebuild and redo all of that work in the compiler again and again. And you could think, can the compiler be smart enough to derive it once and then only share it? And this is like a valid question, because like the word derivation, it has nothing to do with integrals. Like it's like similar etymology, that something is derived from something, so it's called derivation. But here we're seeing that its derivation is because the implementation is derived from the shape of the structure that we are dealing with. If we have a user and we are running derivation, then from the shape of the user, what kind of field it has, what are the types of those fields, and what are implementations for each of those fields for the type classes, we are deriving the implementation for the whole user. So basically, you can just only look at the case class or only look at the sealed trait and assume, okay, there is one single convention used in the whole project, when I am assuming that by default, if I am seeing how those smaller pieces are dealt with, I can assume that the whole part will be working in this way. It should be intuitive. If it's not, then you probably don't want the derivation. You only want to use derivation when it's obvious at a glance from just the shape of the case class, or just from the shape of the enum or sealed trait, how would the whole implementation should work. Okay. But there is this tiny little thing that you always have to look at the scope for those smaller parts. And if the compiler wanted to reuse this user, if the compiler see, okay, in one file I'll need this encoder user, and in some other file I also need encoder user, before it could decide, could I reuse this encoder, it would have to look at all this logic that encoder is doing. So it's calling some macro or some stuff which is building things together. Okay, nice. from what it builds thing. Okay, it builds those things. Okay, it uses the encoder defined in the companion object for string and then builds the encoder for address. Could I cache that? I could if I was certain that the encoder for string is always the same and the encoder for address is always the same. For string, okay, I can decide that it's the same after I take a look at the whole scope and see that it always would revert to the same implicit. So we would already have to cache the whole scope inside the cache just to be able to see if we could reuse the encoder or not. But then we are using the encoder address, and then the same story, happens. So this kind of cache, before we would get to the point when the car decides, okay, we can reuse the implementation or not, probably already have to pay all of that, performance penalty that is needed to do everything from scratch without doing any of cache checking. So we cannot do this cache in such a simple way. We could, and this is actually used. This is what Miles Sabin implemented. That if you are inside the same method, and if you didn't introduce any new implicits along the way, then if you have this nested derivation, this derive, this derive, this derive, this, then if your code see that, okay, here I need string, and in another place I also need encoder for string, here I need encoder for address, in another place I also need an encoder for address, then each of those derivations would happen only once, and then the result would be reused. But that is Scala 2.13. On Scala 2.12 and before, such caching was not happening, and if you had to do this kind of automatic derivation, you could very, very easily have a very, very huge compilation time. So you have a lot of war room stories when someone introduced just simple change in their code, and suddenly their code started compiling 5 minutes from 5 seconds or things like that. And after people spent a lot of the time benchmarking, running flame graphs inside the compiler and stuff like that, they learned that derivation is usually the case. And that's why at some point people started to doing something which is basically like a pointing compiler to a value and saying, okay, if you want to reuse the part, we want you to reuse the part when you are having this, let's say, encoder for address, and I am forcing you to do this by creating manually implicit val encoder address, derive this encoder for address here, and then when I'm using encoder user, I know you have to use this stuff because automatic derivation would be a fallback, and I want to force you to reuse every single of those things. And especially if you have to use the same encoder like here, an encoder or whatever typeclass you're using, and you would have to use in 50 files or in every single file in the project, whatever. People started to decide that, okay, I want to have single file, do all the derivation in that file, and then import the results in every single file with automatic derivation disabled. And then I am sure that I'm deriving everything exactly once, and I'm not paying the price for all of that stuff multiple times. And also, quite often, it also resulted in a better runtime performance because, well, you have to remember that typeclass is a trait, an interface. When we are providing implementation, we are writing a new class. And if we are, summoning some instance ad hoc, this instance, compiler cannot be always certain that it isn't encoding some closure inside. So it cannot just, well, I know this is defined inside a method, but I will move it out of the method somewhere outside because I will reuse it. No. Compiler have to call new on this object every single time. And if there are nested objects, there is a risk that you would have calling new, and then inside object will call new, and then inside object will call new, and etc. So you can have performance hit just from the allocations. And if you just tell the compiler to stuff all of that into some vals, into some object that you would be importing, okay, you are initializing everything only once. And that's how the semi-automatic derivation came to be. You basically wanted to write something like this, Well, skip the type signatures, but let's assume that they are there. That there's implicit val address encoder of the type encoder address, implicit val user encoder of the type encoder user, and people started moving toward this style precisely because they wanted to avoid long compilation times and a penalty, performance penalty when they run this code. So this approach have several drawbacks. Like one of them is that you have to write every single of these lines by hand. The other is that unless you use semi-automatic derivation and automatic derivation at once, there is this tiny little issue. Like when you have this implicit val address encoder, and let's say we want to derive encoder, what would happen if we written here like something like summon encoder address, or implicitly encoder address? Well, the first thing the compiler would do if it was like automatic derivation would be to see if there is encoder for user or whatever. And it would see that, yes, in this code is the encoder for user right here. So we'll use this val right here. And then you are ending up with either, depending if it's implicit val or implicit lazy val or implicit def, you have either like initialization error or stack overflow or null pointer exception. So not really funny stuff. And it's like very, very difficult to work around this because it could all be some intermediate method that would, result in the same like cyclical dependency, but in much less obvious way to the compiler. So compiler wouldn't be always able to like figure it out that this is what is happening.
Yeah, I think those edge cases don't usually happen if you just put things into the companion object, right? Which is the canonical way to do semi-auto.
Yeah. So, but whether you're using compiler object for stalling all of the stuff, or if you're having some traits that will be mixing, whatever, well, this is the real issue that at this point, when you want to derive stuff, you don't want to derive it to this one so that you will not create this implicit, implicit creating this circular dependency which will break your runtime. So when you are using the semi-automatic derivation, you have to implement it in such a way that it is not looking, does this implicit exist? It might exist. Well, usually if you look at implicit scope, then the code here could see that, okay, this value here exists and is in implicit scope if it's like annotated. So then it has to like explicitly ignore it and create a new value. And this is why usually when you see this automatic derivation and semi-automatic derivation, they have usually, not always, but usually separate imports and separate methods used to create the stuff.
Yeah.
Yeah, but the problem is that, well, no problem, it's usual convention, but if you are ignoring this user here, and then you are trying to look for all the imports inside, I encourage it if to our listeners, if they want to do some exercises, try use shapeless to write such a derivation, semi-automatic derivation, which would ignore the type that we're deriving right now, but will not ignore those types. Once they see those types inside, like for instance address, we try to derive them recursively. It's a lot of pain. I would say that usually ending up those mixed approach when you have separate implementation for automatic derivation, separate implementation for semi-automatic derivation, and you have to be very, very careful to not mix them together so that this code here would not so that by making it recursive here, you wouldn't accidentally unignore the implicit here breaking your stuff. So it's really, really hard, and I guess that's why, or at least it's not very, very intuitive. You can design some ways about doing this, but at this point, you are going inside the macro magician kind of stuff when people don't want to be. So usually, for the sake of simplicity and having easy to maintain code, people simply not do this. They have one piece of code which is automatic, one piece of code which is semi-automatic, and then tell their users that if you have to have recursive derivation here, like if you don't see the address and you want to have it generated, have this another import with automatic derivation. If you don't have this another import, which which will force your user to start thinking which part is done with automatic, which part is done with semi-automatic, and all of that, then usually you're ending up with something like this when you have to write implicit val for every single intermediate type.
Yeah.
So that the final line would be able to compile, because it would pick up all of the stuff it needs to build this bigger, large implementation. It's not required. As I said, you can also have this thing and somewhere above it import for automatic derivation. But good luck explaining it to juniors. Like to your junior, why you did this, why you have to do this, why it looks like
like that. I guess most people just, in most projects that I've seen, just give up on the complexity altogether, and just decide, okay, we are never using Koto. We are always just using semi-auto. If you have a compiler that implicit is missing, so it's a missing encoder for, let's say, address. Okay, that means that you go to the address, you go to the companion object, and you just type that implicit val or given encoder of address equals derive. And that is the magic spell. It just solves the problems. And I think it solves most of the problems. At least it did for Scala 2, right? So I think the biggest difference is that between auto and semi-auto is just semi-auto just gives up if it doesn't see a predefined implicit. It has to be defined
like those two
for
things.
a member.
It gives up if it doesn't see this predefined implementation. So you have to provide it either manually or by this input of automatic, and that it doesn't work as a fallback. It will always try to create this new instance to avoid this cyclical initialization errors. Those are the two main differences. And yes, to a degree, you could work around all of it. Like a lot of people do this the way that they are creating those instances inside their companion objects, and every single companion object has this instance defined.
Yeah.
Of course, you have to be aware that this has this tiny little drawback. That means that your definition of your data has to be polluted with the implementation details for the encoders, decoders, and whatever you're going to need.
Yeah.
Because every single type class that you want to use, you'd have to put implementation inside your companion object, assuming that you can even do this. Because sometimes you have some shared libraries in bigger companies, and then you cannot really edit someone else's code. And also you might have, okay, this code is domain code. We don't want anything there. And then some other team decides we want to have show pretty, because we want to have this pretty print with those nested stuff in our logs because it's easier, it helps us, etc. And so you're gonna convince other people that they should do derivation inside their companion object so that you will be able to have pretty prints. It's not gonna always work. Very often you can if you're the only owner of the repository and everything is inside a single repo and there are no multiple packages, when you don't want to split different layers of the application like the persistence and API, etc. And then
Yeah, sure.
But sometimes you could use this approach when you shove everything in a companion object, but you don't always have this ability, and you cannot assume that all your users will always be able to, because that's pretty much sabotaging the library if you're assuming that.
Yeah, I think Scala 3 also decided to go this way, because we have the derives clause right now, which basically boils down to semi-auto. What derives does is it just creates a given inside of the companion object and calls the derived method, which is defined on the typeclass companion object. If I remember that correctly, I hope I do. So we already have some bias towards using semi-auto, and there are those reasons that you do pollute the types that you might want to have them clean. So it is a bit of a trade-off, I would say. But I think that everyone is happy to some degree in Scala 2 with the basically not the plateau, but I mean consensus. So the consensus seems to be that semi-auto is the way to go, and based on the popularity of this approach, how well it worked for Scala 2, we now have derives, which is basically the same thing, but just in the language. So let's jump into your proposal. What is the difference? What did you do in Chimney, and what do you propose that we do that is different from how those two approaches work? Both of those approaches are used in Shapeless and also Magnolia. I think both of those libraries propose an automatic way and a semi-automatic way. How is your approach different?
So our approach, originates from Chimney, because Chimney, as I said before, is a library which handles like data transformation. You have some case class here, you have some case class here, and you want to have as little hassle to convert one of them into another as possible. And usually this is not something that you want to tie to a single place of code. Like you could write some method like convert like DTO to the domain class and domain class to DTO, whatever. But very, very often this kind of stuff is only done ad hoc on one single place. Like for instance, let's say you're writing controller for your HTTP server, and this controller is going to call some domain method, domain stuff. There's a good chance that this JSON encoded to some case class, and then this case class converted to some domain type, is the only place in your whole application that you would need this conversion. And for this kind of stuff, people would find it like, kind of bothering if they had to, do this semi-automatic stuff when they would have to do, derivations for intermediate types, especially since this kind of conversions are usually, heavily customized. Like 99% of the code is generated, but you have this 1% when you are saying, okay, this field is renamed, this stuff is this. And as far as I remember, Derive only handles the derivation where you cannot customize things. So that's one of the reasons. The other issue is that Derive only works for the type classes which has a single type parameter. Chimney, by definition, need to have two, because you're generating conversion from one type to another. Mm-hmm. So you also have to have two types, like the input and the output, source type and the target type. So that also like sabotage any sort of derives. And three, well, usually people want to have this separate implementation when either they reusing this. And for one of things, the overhead is not really like if your goal is to remove the boilerplate and then you have to create some boilerplate in order to use it, it's not a convincing case for people to actually use the library. And the other thing is that usually if you creating a separate implementation is because you want to write a unit test for it, so that not only is used in this piece of code, you also have a unit test to see how it works. And at least for Chimney, not always, but usually I find myself that I don't really care how I created this code, whether I've written it by hand or written with Chimney or written it whatever other way. So I usually have some place which are using this code. Like, let's say you have a controller, you receive some JSON representation, and this JSON representation is calling some backend. If I write unit test, function does integration test, which test does logic. If I send this JSON here, is it translated to this call in the service inside? Then I don't care if I generated this code with Chimney, or if I written behind, or if it was generated by some ChatGPT or whatever, or if it was written by unpaid interns. I don't care. I only want to care if it does what it's supposed to do, and if it does what it's supposed to do, and tests are the things that validate that it works the way it should work, I might as well generate this code with macro or whatever.
Sure.
And not test it anywhere else, because this is the only place that I need to make sure it works. So there are other cases like that when you don't really have a business in testing this side of code. So unless you would have to derive it in 50 places and then make sure that every single of those places is using the same implementation, like creating a separate implicit and then testing it and whatever, it's sounds like a big hassle. Like, let's say you are using Tapier.
Mm-hmm.
If you're using Tapier to define your endpoints, and then you are testing those endpoints with some integration testing or whatever, like, I'm sure that you are testing these things, and you want to test these things because even if the JSON derivation is free and you want to do this because all this compile magic, make sure that those things will compile and work and it will not blow out in the runtime. Every single JSON library I came to work with had some tiny little stuff that would catch you by surprise. And even if it generated the code that is supposed to work perfectly, if you want to make sure that with every single update your code works the same way and it works as you want it to work, you always have to write this integration test when you are sending is the string and see that the string is handled correctly. So it's not an argument for anyone I know to stop using typeless derivation for JSON. It's just an argument for everyone to start testing their code. But well, yeah, that as far as I care, creating those stuff and writing a bunch of derives in some cases might see like a writing boilerplate, because like if you're using Tapier, there's a good chance that you would define some stuff in one place, auto derive some JSON encoder, decoder, whatever, let it use inside Tapier, inside some body, JSON body or whatever, reuse that value, because usually people are starting to refactor in their code, even if it's like Tapier or something like that, and after a while, well, they are reusing the implementation, even though they are not reusing implicit vals like explicitly. So also, good luck explaining to juniors why you have to do a bunch of derives and all of this stuff, and telling them you have to do this for this stuff to work, and then someone is using another library and they are not using any of this stuff and it just works. Yeah, so for us, it was really, really important that automatic derivation would work out of the box, but without imposing any sort of performance penalty for the users. And so at some point, we noticed that when you're doing this recursive derivation, doing everything as much as possible in macro, then it really helps with compile times, provided that you're not retriggering this in one automatic derivation, another automatic derivation. At some point, we have this, temporal solution. I think it was Scala, Chimney 0.7 and before. We already noticed that this recursive derivation have amazing value for the users, because if you are doing everything at once, like in depth, you are able to provide very, very good compilation errors. You are able to tell your user that in this path here, this is place where it breaks because you don't have, some definition, you haven't provided something or whatever.
Yeah.
And you can provide all of it at once. Meanwhile, if you have this approach when you have macro, handled like only like one layer, and then there's this nested type handled by macro, which handles only one layer, and this is another, etc. At best, you can say, I haven't been able to find an implicit for this field. Why this field? What happens? You cannot give user very little information what failed. So, and also, like if you was this type which had two derivations and then have two another derivations, and you have one failure here, one here, third there. Yeah. You wouldn't be able to tell users at once there were like 3 failures. You could fix them at once, and then it's gonna work. User would have to try to recompile their code 3 times, separate times, to figure out all the stuff. If they were using automatic derivation, with semi-automatic derivation, they would have this information if they were using Magnolia, what failed. But every single implicit val have to be written by hand. So in some cases, it's absolutely atrocious, like UX. And the other thing is that once we notice that we want to give users very good error messages, and this very good stuff, so we should avoid called retriggering macro automatic derivation macro from itself. So our initial approach was that we were actually retriggering this macro from itself, but we were taking a look at the generated tree, and if we saw, okay, this code was generated by us, so let's discard it. And that's how we ended up with this, exponential compilation times in older versions of Chimney. So we had to address that. We wanted to give people good error messages and also good performance, because if you are able to decide what to inline, what not to inline, what to put into separate def nested inside your class, and etc., you're getting rid of all of these intermediate locations, so people can get really kick-ass code, kick-ass performance. Also, in case of Chimney in particular, like we have those distinctions between total transformations, which always works, and partial transformations, which are like, let's say, transforming into a combination of option, either, and try, because
they might work.
They might work. You're guaranteed that the compiler guarantees that failures are handled, but some particular pieces of the transformation might fail, and you will receive a very detailed information where it fails. But then we had an issue. Okay, so some of the smaller transformation inside might be total, some might be partial. So we have to we can always lift total transformation to partial transformation, but that would mean that we are always boxing, and you could end up in a situation then not a single part except a tiny little one fails, and still are boxing everything, and they're using something like map2 from stats or mapn or whatever. Even though you could just get rid of all of that, because you could generate those unwrapped smaller values and only combine them with a single map or map2 or whatever.
Mm-hmm.
So this kind of optimization would be really, really hard if we have to summon partial transformer. And since because we are doing things recursively, we can decide, okay, I was able to resolve this smaller subtree of this sub expression of this whole expression, and it's a total, not a partial, so it's not wrapped. So I don't have to wrap on rewrap on map it at this point. I will pass it to this higher level, and it will decide what to do this. And on this higher level, okay, so we have several values which are unwrapped, only one which is wrapped, so we use only one map, and this way we are avoiding this allocation, reallocation, all that stuff. So if we move to this approach that you have here, so every single intermediate type has to be a separate implementation which is wrapping all of those details, you can no longer do this optimization. So you always have to pay the performance penalty, because you're losing the details which will allow you to optimize the stuff. So that was another big reason that why we wanted to avoid calling ourselves inside our macro. And so during the migration to Scala 3, we wanted to preserve that, but we also wanted to deal with this issue that okay, our compile time is exponential, and through a lot of trial and errors, we figure out that okay, so basically we want to have this principle that macro is recursive. Built-in support for built-in tabs is defined inside a macro, so it doesn't need another extra implicit. It doesn't really need some extra implicit search. We only want to use implicit to override the behavior, and now we have to find a way to how to implement it. And for us, it was obvious that we want to prevent macro from calling itself. Like, it was important to have those principles preserved. Similar thing is done by JSON-ter, because JSON-ter, treasure performance above everything else. Sometimes also user experience when it comes to API, but they wanted to have the good performance, and they have it. But the way they achieved it is that, okay, we also want to have a situation that we are doing things recursively because it's performant. We want to handle built-in support for built-in types internally, and how they avoided calling themselves inside a macro. Well, they simply do not support automatic derivation at all. So you simply have no way of using JSON with automatic derivation. If you provide yourself in some way implicit for automatic derivation, performance go to hell.
Okay.
So, but we wanted to have this ability, but without making performance go to hell. So we figured out, okay, so if we had two types, one is the subtype of another, like let's say, okay, this is subtype. Let's have with.
I think we can use a concrete naming from Chimney just to make things
easier
to understand.
In Chimney it was like this transformer and transformer auto-derived.
And which is subtype?
The auto-derived is a parent of the
okay.
not derived.
Okay.
This, which is counterintuitive, especially if you have this reasoning that this is always this, because that's how the arrows work in OOP, but here we are kind of abusing the system. So basically we're doing something like, okay, this every single transformer is an instance of transformer auto-derived.
Mm-hmm.
So if I need to use transformation, I can summon transformer auto-derived, whether it's like user defined it or compiler provided. I'm gonna resolve it, and that's how our extension method works. But when compiler is generating, transformer with semi-automatic derivation, automatic derivation, whatever, then this macro is, I always want to transformer, never transformer auto-derive. So the more specific case, which means that the implicit, which provides auto-derive code, is never found, it's never resolved. And this way we are able to basically avoid this problem. But of course, this an implementation that is kind of leaky, because now you have two types in the API, and if user wanted to provide some custom behavior, they have to be aware of this stuff. So ideally, if the compiler give us some ability to basically have the same benefits, but without all of this splitting of types, just give me this implicit, but ignore this implicit. Just give me an instance of this type, but ignore those implicits. If I had this ability, I could simplify the API. And I also believe that other people would also find it beneficial. If you take a look at the numbers, because from my own experience, if you have this automatic derivation, is much better user experience, because you have some opportunities to optimize the runtime. Compile time is also usually faster if you try to not ping compiler too much, and errors, you can basically generate nested errors for nested types. So you have this ability.
Could you maybe show us how this proposed approach that you do work? I believe you had a chart for us.
Yeah. So basically, when you compare derivation with this recursive macro derivation, this one looks kind of more scary, and that's because here, every single type, if you want to find handling for a subtype inside a field tree, or handling for a field inside a case class, you're always delegating it to implicit search. And if you have any sort of if-else logic, I want to prefer this behavior to this behavior to this behavior, etc., also done with implicit logic. So all of that is basically shoved on the typer. Okay. Both on Scala 2 on shapeless, and in Scala 3 when you're using mirrors with all this inline ifs, inline match, etc. If you are doing this in macros, then you have this very same idea, but you're not calling for implicit. You just see, is there an implicit? If not, then I'm gonna call myself recursive, as a recursion inside a macro. So this is, this tiny little change that if I see, okay, there's no implicit, I'm not giving up. Instead, I am handling inside the macro recursively, trying to derive it and get some either if it failed or succeeded and whatnot. And also this implicit search right here is gonna ignore call to itself, while with Circe or all the shapeless-based libraries using typeclass, astronaut, guide to shapeless, have this approach that it's always dumped on the compiler and the typer and in places. So if we take a look how like JSON inter would derive like the codec for address and the user, so it would work kind of like this. So first of all, we don't have an automatic derivation in JSON inter. So it's always creating a new, when we are deriving new codec, then it would always like create a new one.
Yeah.
So you would take a look. Okay, is it a user case class? Is user a case class, or is it like a sealed rake? Also, like if this macro is also like handling those built-in types like lists, maps, strings. But for the clarity, let's skip that. We only just take a look at case class. Okay, and JSON inter C. Okay, yes, it is a case class. It has a field name of type string, field address of type address. Okay, so let's take a look at each of them one by one and see if we can handle them. Is there an existing encoder for string? And JSON inter does not provide. Sorry, no, I should have changed encoder to JSON value codec. But is there a JSON value codec for string inside the JSON inter? And JSON inter says okay, no, because I am not defining any instances. Okay.
Really? I think they Android does provide instance for string.
No, he doesn't. There is not a single instance.
Yeah, but it's built in. Oh,
it's built in, right?
Right.
So
you're correct.
Yes. So then, what JSON inter does? Okay.
Yeah.
If there is no implicit with JSON value coded for string, is there a built-in support like here in this library? And okay,
inside of the macro, right?
Inside the macro. Okay, so I'm gonna use it. And then it takes a look. Okay, the next field is address. Is there an implicit with address? We haven't defined one. And there is also no automatic derivation in JSON inter. So it also ignores, okay, there is no. But is address a case class? Yes, so let's try to handle it inside our macro. So all of that is happening inside a single macro expansion. As opposed to this stuff when this is one macro expansion and this is another macro expansion.
Sure.
So then it's see, okay, is there a way of handling a string? Yes, there is. We already went through that. Okay, and is there a way of handling like address? Address has only one string. Okay, so we handle all of the fields. So we combine the handling for each of those files together, and we this way we create that. No, not a new trait, because like here, we would create a new encoder. JSON inter doesn't do that. This instead creates devs inside this single single type class, and they are calling those devs.
Okay, so inlines those methods to encode a given type as just methods inside of this instance, the single instance that is created.
Yes, and it also has this tiny little property that if you have inlining all of those type classes as devs inside a single scope. With devs, you are able to handle recursion without creating a new object and etc. Like with CRC usually or CSS and with shapeless, you usually have to work with this thing called lazy.
Yeah.
And this is the way you would handle like recursion and stuff. So another thing you have to worry about as a library author. But anyway, we have handled all of the fields inside address with devs. So we are able to create a dev handling address. So we are handled all of the fields inside user, and so we are able to generate the whole implementation for JSON value codec for user. So we are creating a single type, which internally handles all of those intermediates, all of these intermediate types. Sure. And also, if we wanted to, we could override like the behavior, provide our own implicit, and it would be used. But if it's absent, the library is gonna, handle itself like easily.
Sure. I just wanted to add a quick question because it was something that was bothering me a little bit. Who was first? Because you are showing the semi-automatic approach, the version of your approach based on the JSON editor. Was JSON editor first or was Chimney first?
As far as I can tell, JSON editor was first. Like, I haven't looked at the code of JSON editor version 1, but the version 2 point whatever, I think they already had this sort of approach. So they were doing this for several years now. This, like, recursive derivation approach. We were thinking about it before, but until we figured out this, tiny little detail how to, prevent ourselves from calling ourselves.
Yeah.
With JSON editor just simply, not support by definition. Until we figured it out, we didn't even try to do like this in this way. So JSON was clearly the first, as far as I can tell.
So another question, because this is a semi-automatic approach, right? How does this differ from the approach that you mentioned before, which is the automatic version of this?
If you are comparing like this approach to like this approach.
No, I mean the automatic version that you have in Chimney.
Oh yeah, in Chimney. So the difference between this and Chimney is that in Chimney we define things in such a way that you would at first try to see if user is like, let's say that this is the input for like Chimney macro. So first, I would the code is defined in such a way that we're trying to take a look if you have defined your own transformer. If you haven't, then we are falling back to this transformer auto-derived, and then all of this magic happens. And then if in each of those things, like, is there an implicit for this? Is there an implicit for that? Is there implicit for this and this and that? Because we have the split hierarchy, it would only look at those transformers which are defined by users, either by hand or through semi-automatic derivation.
Yeah, so it never looks for the auto-derived type.
Never looks for the auto-derived. This is super important, but without this, a lot of things like goes to hell.
Yeah. Okay. Yeah, that makes sense. So let's recap that a little bit. So we have had the approach that is still being used and is quite popular in Scala 2, which is Shapeless and Magnolia, which offer semi-auto and auto approaches where, auto isn't very nice because it generates heaps of code.
So,
Oops. And the problem is that they actually go through the typer. They go through the compiler to retrigger the macro itself. So macro calls itself for all the types that it has to handle. It has to compose. And that happens in auto. In semi-auto, it just gives up. If you haven't defined an instance manually, it will just crash, but it will crash with the error from the top level value, right? So so there is no information about, okay, which instance was missing. You don't get that. You just get, okay, so the whole user, it just failed. You can't derive that. And then there's this approach that JSON editor uses and Chimney now uses, which basically never leaves the macro itself. It just takes it just looks for implicit instances that user might have provided, but most of the time there won't be an instance like that because the whole thing is to do as much stuff as you can in an automatic way, and then it just uses itself. I mean, it uses the code that was in the macro, right? And uses the instances that were built into the macro. So for primitive types, you have your own instances that are built in. But you can override them if you provide the instance of the subtype, of the transformer in this case, right?
Exactly. Okay. So the idea is that user is always able to override behavior by providing their own implicit, but we are, trying really hard to not mistake, not confuse their overrides with the methods we are providing, because there is no use for us to call ourselves. So as much as we can, we are avoiding calling it ourselves, because having everything, in one single macro expansion, in one single context, allow us to optimize things, provide better error messages, and also save some CPU time when you're compiling stuff.
Okay. So I have to say that initially, when we talked the first time about this, my assumption was that JSON editor, given that it has those complex macros, same as Chimney, it has to compile in a slower way. There's a lot of more stuff happening in the macro, in contrast to what happens in Magnolia-based libraries or shapeless-based libraries, which basically they just list types, check for instances in the implicit scope, then just glue them together, all done. Well, you have full-blown macro, so I assumed it has to be slower. Could you show us how the numbers actually look like?
Yes, not necessarily for Chimney, because I don't have benchmark comparison to other libraries, because there are not much libraries like Chimney.
Yeah,
there are some, but let's take a look at something which is more familiar to people. So one of the comparisons I was making during my presentation is comparison between CRC and JSON editor. So because compilation is something that you are handling in two use cases. Either you are having a call JVM, because every single time you're compiling things on the CI, you always have call JVM, basically.
Yep.
So if you want to save some time waiting on those results, you have to pay attention. And the other thing is hot JVM, if you are using something like SBT and you keep things in the same shell or bloop when you are keeping JVM warm. So that's why I was measuring how the same piece of code was behaving when there was hot JVM and cold JVM. So I was also comparing Scala 2.13 and Scala 3.3.
Yep. LTS.
So yeah. So I have found out that on Scala 2.13, the numbers when it comes to compilation times are not that different where you use automatic and semi-automatic derivation. If you only need this implicit in a single file, like if you wanted to derive the same stuff several times, like 10 stuff, from scratch, of course you would notice the difference.
Yeah.
But if you only need ad hoc in one place, there's not that much difference between automatic and semi-automatic derivation. That's the things I saw when it comes to CRC generic, which was implemented with shapeless.
Yeah.
There was also CRC Magnolia, but
yeah, if I may, there's a big caveat. I would like to underline that, because with auto, you will pay this price tag multiple times over if you have the same instance being derived in multiple files, right? Or even multiple scopes. They can have different scopes, right?
Yes.
Yeah.
So there's the difference. Of course, if you have single derivation in a single place, and then automatic versus semi-automatic is not that much of an optimization. If you are reusing the same stuff, then you will notice some differences. Although in my experience, quite a lot of those type classes are only used in a single file and nowhere else. So and those type classes that you want to reuse in several times over, then usually you also want to have the same consistent behavior between them, and then much longer before the performance comes to mind, you already are thinking about consistency of your application, and that is the reason you are reusing these instances.
Yep.
And that's not a use case I want to challenge, because it's very, very really valid.
Yep.
But so when I was comparing, this one is CRC generic with shapeless, and this is CRC semi-automatic with shapeless. So I created some really nasty use case, really nasty case class. I made sure that this case class is compiled in a separate compilation unit. Not all of the libraries I would be using are also in a separate unit. So this test will run in a file which contains a single main, deriving single encoder. I needed a single encoder and a single decoder, and run something like a round trip. Get this value, instantiate it, like encode it and then code it, and I want to know how much this tiny little file compiles, and what is the performance for each of these approaches. So there isn't that big of a difference between automatic and semi-automatic derivation Scala 2.13. Like you see that Mas 7 actually did some work to make sure that those instances are recached and reused, and so the code is not that much different. You could see that the difference that Magnolia provides is there is some. You could see that those bars are slightly lower. So you could see that whatever Magnolia does, the definition of this stuff you're doing at runtime is giving some benefit, but it's not super drastic improvement over shapeless. At least on Scala 2.13. If you are still on Scala 2.12, you might see completely different numbers. On Worm JVM, you see that those bars are slightly slower.
I wonder what the error threshold is here, because
like it's very I guess someone would have to make a lot of these tests and provide them. I only knew I could tell you that I was rerunning those tests again and again and again. I see that the numbers are changing.
They're stable. Okay.
Numbers are slightly unstable, but there was no big
I'm only asking because Cersei Magnolia being fastest is kind of surprising, especially given the semi-automatic is slower on hot JVM.
Yeah, that was surprising to me. I ran it a few times and I saw that this result
it wasn't an artifact.
It wasn't an artifact. Exact numbers were changing, but the trends were preserved. So that surprised me. I'm not really sure what happened here. So
interesting.
Yeah, that's interesting. But I guess that's something for compiler developers to tackle. They're curious.
Yeah.
Yeah. But there's much different history when we take a look at Scala 3. We can see, because there we can see that automatic derivation, and here it's not done with shapeless, it's done with mirrors. Then, well, it's much worse. You can see that the performance of the automatic derivation with mirrors, it's it's no longer something like let's say 15 seconds. Is more like 46, things like that. So yeah, kind of nasty stuff.
So Cersei generic and Cersei Magnolia automatic, they are using on Scala 3, they are using mirrors. Am I getting this correctly? Okay.
Yes, I was curious why the Magnolia is slightly better on Scala 2.13 and much worse on Scala 3. And I've learned reading the code that Magnolia on Scala 3 is based on mirrors, while on Scala 2 it was based on macros. So on macros, it was written from scratch to be performant and compile and perform as good as possible. While on Scala 3, I can only assume that the issue was we want to have Magnolia on Scala 3 as soon as possible because we are blocking people, and the easiest way to do this is with mirrors.
Yeah.
And then probably nobody did a benchmark because Magnolia was supposedly faster than shapeless, and so it should be faster than yada yada yada. So only after those benchmarks, I guess people might have started paying attention that maybe we need to rewrite Magnolia on Scala 3 to use raw macros or something.
I would say that there's a different thing that is kind of important here in these results, which is that mirrors probably need some optimization. I mean,
I wouldn't say that mirrors itself. If you look at mirrors, well, mirrors you are basically just a trait with a bunch of nested path dependent types that you are shoving to those inline defs. So
yeah, but what do you think is causing this? Because the result is, in comparison to Scala 2.13, is well, it's abysmal. It's over 45 No, more.
Yeah, so I can only guess that we are doing a lot of things in Scala 3 with inline defs. And then we have, inlines, summon inline, we have this summon all, we have inline if else, inline match. So I am guessing this erased value, and all of them, use when you start working with this, derivation, whether automatic or semi-automatic in Scala 3. And my guess is that once you are forcing your typer to do all this if-else logic, pattern matching logic, exhaustivity checks, like inside, not in the generated code even, but on the when you are still deciding, do I want to tell this code that is type checks or not? Then probably you're forcing the typer to do so much work that probably just simple implicit search that we could show on Scala 2.13 was easier on the compiler.
Okay.
We're forcing compiler to do much more now, because now you have implicit search and all of this inline stuff, which basically is happening inside the typer. So typer becomes the interpreter of your code.
Yeah.
So
okay, that sounds like something to look at for the compiler team. Okay.
Probably.
Okay, I see that JSON is doing pretty well in time.
Yes.
In terms of compile times on both Scala versions.
Mm-hmm. Yes, as far as I can tell, the fact that everything in the compiler is resolved internally. Like, you don't have to ask the compiler, okay, if I want to do this if-else logic, compiler is going to tell me what is if, what is else, because that's how implicit you are working on, shapeless, when you have to basically encode everything using implicit priorities and learn what are implicit priorities, so that you know that this is used and then this is tried and then this is tried and this is tried, so that there are no ambiguities, because unless you take care of those things, then you have to have really hard time to make sure that every two implicits are mutually exclusive and compiler will not mistake them. But still, if you took care of this implicit priorities, and you have this if-else logic, or more pattern matching logic when you are going through each of those cases. But it's like a single point that you have to optimize, and apparently Miles Sabin did a really good job with it. Mm-hmm. On Scala 3, you have implicits, but you also have inlines, and this inline def, there's inline if, there's inline match, you have erase the values, you have all these compile ops, and apparently when you are actually forcing compiler to do all of that stuff, then probably compiler could inline a lot of things to create some performant code, but you're basically running interpreter inside your type checker. So
yeah, I get it. Okay, so we can see that numbers are pretty good for your approach, actually. The semi-automatic is the automatic version, which is you only run it for Scala 3, right?
Yeah, to test how the semi-automatic approach would work with JSON eater. Mm-hmm. Let's say I wouldn't be able to just merge the code to this JSON eater repository and test it. So it was easy to just wrap it and test how this wrapper perform, even with this tiny little overhead of wrapping one type with another.
It looks pretty good.
Yeah, so there is some small penalty, but it isn't much. And as you can see here, even with this, it's just a wrapper, it performs better than Magnolia, comparably to semi-automatic approach of whether it's Mirrors or Magnolia. But consider this new automatic derivation, which is on pair with semi-automatic derivation, when you have just import, use the stuff, and you don't have to care about right calls, implicit vals or givens or whatnot. So that's a quite good result as far as I can tell. So yeah, I only implemented it in Scala 3 because on Scala 2 I would have to use vampire macros. And
okay, let's not get into that. Sounds funny, but sounds also like a very, very deep. Okay, so it looks like there are mostly upsides. But I'm curious, what are the downsides? What are the problems that you can already see with your approach? Are there any? Or should we just rewrite everything to your approach?
So obviously there are issues like in order to not call myself for my macro to not call itself, I have to do this work around this weird dancing of having two separate threads. Of course, life would be like too easy if you have a simple solution and make sure that it's gonna work forever. Which is why Scala makes it much more entertaining for me, and it basically changed the way the givens are gonna work since 3.7, which means that this approach will basically stop compiling if you start providing your own semi-automatic values. Like if you write your own transformer and then if you put it inside your companion, then the compiler will not even look at implicit parameters and see, okay, I want to prefer this to that. It will say, this is ambiguous. You have to write pick your type class yourself because I'm not gonna handle this. It would work only as long as you would be using implicits everywhere. And I checked that by implicits everywhere, I mean that I am defining all basically. And not only that, I mean that I would have to make sure that my users are defining all of those implicits as implicit val. And if they are summoning them, they have to write implicit in the in the method definition, the declaration, because if there is a given or using anywhere, we're switching to this new semantics. And so even if user just switch in type parameter implicit to using, it already breaks things.
Okay. So since 3.7, the fact that you have this hierarchy and you have a supertype and a subtype, and you only summon the subtype, right, from the macro, it will now cause an ambiguity error in compile time.
Yes. So it's not a good user experience. I have several ideas how to work around it because, as I said, I have those two things. For me, it's an implementation detail. I only want to be able to prevent myself from calling myself. So as long as I have some other way of doing this, which is not gonna break in next 2 years, I'm gonna be happy.
Okay, so you mentioned a solution that you wanted to have, like summoning, but with ignoring stuff, right? Is this this the answer?
Yes. So for me, it would be perfect if when I'm writing a macro, instead of like the other stuff, which is like exproof dot summon name of the type, and I receive the exproof the result value inside an option, because it can be a result or not. So for me, it would be ideal if I could have some ability to say something like, okay, I want to get implicit of this type, but please don't even try to look at this and this and this and this symbol. Don't try to type check them, resolve them, see if they are eligible, implicit, whatever. If you when you are just starting building the list of what could be the possible implicit that would be resolved to this, ignore those things up front. If I could do just this.
Yeah, basically summon, but ignore the symbol of this macro, which is currently being expanded.
Yes. Just a single simple method inside the quotes, and I would have a single type class, so a single interface. Transformer, no transformer auto-derived. Easier for users is to use. Also, I believe if other people would try to use this same approach, it would also simplify things, because there's another downside. If you are using this Derive approach, when you derive code which is type parametric, then let's say that we have encoder from CSA. Then when you write like user derives, and let's say like this user is type parametric, it's user of a something. Then you write derives encoder. The code you would get would be something like a given, open square brackets, this type parameter, double dots, encoder, and then the generated code, because this, so that each of those fields inside which would be using this type parameter would use the encoder which is provided this way.
Mm-hmm.
And there is this issue that if you have those transformer and transformer auto-derive, if you would try to derive transformer, that it would only take another transformer, which means that it would not be able to automatically, fetch those types inside. But if you read something like derived transformer auto-derived, that's gonna work, but it's not as super useful for your users, and also it would return the type transformer auto-derived, which would be ignored by other macros. So for me, it would be the best if I could just in my macro don't do this workarounds,
Okay.
and make sure that because I have to admit this is the issue that derives breaks if I try to do this in a split hierarchy.
Yeah, but those things sound like very deep edge cases, don't they? I mean, for a mortal, let's talk from a mortal perspective. How hard is it to implement your approach?
How hard is to implement my approach? Well, the biggest issue for any mortal is that you would have to learn macros. So it would be best if there would be some macro libraries which makes things better.
Okay.
As a part of the search development, I did something like that. I created myself some like standard library, let's say, for macro derivation, which is Chimney Macro Commons, which also let us reuse some utilities between Scala 2 and Scala 3.
Okay.
But of course, we are still working with macros, and this library is still like, Chimney is not a typical, macro library that you could derive using Magnolia, because you have two type parameters, which means it's not optimized for all those cases that usually people have, like when they're picking Magnolia or things like that. So I guess it would still be possible to provide users something like easier to work with.
Yeah. Okay. So it means that you have to pay the complexity tax.
Yes.
On the library side, but not on the user side.
Like my personal opinion about the current state of art is that we designed the system which is heavily biased towards library authors, because whether you're using Shapeless or Magnolia or Mirrors or whatever, you can just see one presentation, do one stuff, etc., and you can easily start writing this kind of libraries. But it's very easy for you as a library author. But if you wanted to provide, let's say, meaningful compilation errors, things are starting really iffy.
Yeah. Implicit missing basically is the only way to provide errors.
Yeah, if you wanted to have some, customization or optimization on stuff, things are also becoming kind of hard. So usually you're not doing this. So usually your users are paying all of the stuff. If you are your own users, then every single time you have issue, you just modify the library. But if you have some upstream library and use just a user, well, there's not much you can do. So most of our libraries have, implicit not found as the best error messages. Sometimes you can have information if you are using semi-auto everywhere. That the issue is this field because I don't have a typeclass for this particular field. But that's again the best you can count on.
Yeah.
So, and of course, there's no possibility to optimize the performance. If you have used all those intermediate instances, there's no way of optimize the compilation time. So, basically, the current approach is that it's easier for a user to write a library than for the library user to
to use the library itself. Yeah.
To use the library with good user experience.
Okay, so the follow-up question has to obviously be, how can I learn this power? I mean, what is it completely necessary to go through the whole journey that you did with Chimney to understand all of that, or would it be possible to, I don't know, build like a derivation kit for macros and make it more, mortal friendly?
I believe it would be possible. Like some first steps are like when you take a look at Scala Land, the organization where we have Chimney in, there's something like Chimney Macro Commons templates. So I have a template repository that you could use to basically kickstart working on some type class. Unfortunately, we cannot skip the part when you're learning macros, but it provides you some stuff, and from there on we could start building to provide some much better API when it comes to all of this stuff. But I guess some research would have to be done. Some goals have to be decided what we want to get, and someone will have to pay for it, because it's not something you can do after hours. It's gonna take you half a year to improve the state of the art for the whole community. So
yeah, I get it. I've seen the template that you mentioned, which uses the Chimney macro commons, right? And
exactly.
it's kind of gnarly. I have some understanding of how those things work, but it's still
I agree.
Not easy to jump into that.
Yes, I agree. Which is why everyone is using shapeless mirrors, Magnolia, because
usability. Right?
they're much easier to work with. But again, it's for me, it's like a rapid prototyping for meta programming library. It starts very fast. You just get a fast feedback how things are working on. But at some point, if you wanted to improve things for your users, not for yourself, for your users, then it starts getting in your way, and then you have to learn the hard things.
Okay, so I guess it is quite impressive in terms of, and surprising, by the way, in terms of compile time, performance, and the end performance. Given that, is it sane to assume that JSON editor is that fast in runtime? I mean, because of this technique, or maybe it's just a factor.
Well, JSON editor provides several techniques, so
so it's a factor, probably.
It's a factor, but we can take a look at that other runtime performance, and you can see that JSON editor is 3 times faster in the runtime through all of the techniques, so they're clearly paying off. But you also have, when I was doing this benchmark, I was also kept in mind that I need to point out that this benchmark is actually kind of biased towards Circe, because when I'm doing this round trip, I'm taking JSON data type. I'm taking
not a string.
I'm taking a case class, converting into that JSON data type, and then I'm parsing this JSON data type back to this case class.
So not to the string.
JSON editor starts from the string. So if you had this idea that you are using JAWS parser to convert strings into the JSON, then JSON is decoded, etc. This difference would be much bigger.
Oh, wow.
But that's one of the other techniques that JSON editor uses. It does not use the intermediate.
No AST.
JSONs.
True.
No AST. So those benchmarks are slightly skewed towards Circe because of that. And if we took a look at something more which isn't apples to oranges, I also implemented something like a pretty printer type class, and then I implemented it in Magnolia, in shapeless, mirrors, and finally with macros with automatic derivation. Are these the final? Okay, I think it's the naive approach. And after that, I also did optimize approach. And when I'm using the same thing as JSON, we're just storing intermediate results as defs inside.
So you're caching instances, basically.
My caching instances, which is not something you could easily do without creating, a wrapper.
Yeah.
So in this approach, basically the sanely approach is always winning.
Wait. Did I understand that correctly? The previous benchmarks for Circe versus JSON editor, the wrapper was not caching instances.
No, sorry. JSON was caching. Those are different benchmarks.
It does that.
Those are the benchmarks for the JSON editor is in fact caching the instances as a defs inside.
Okay. So the result is it's basically it's hard to compare how fast that is. The only thing that is comparable on Scala 3 is semi-automatic on generic. I guess that is mirrors, pure mirrors.
When you look at these numbers on Scala 3, then it's semi-automatic Magnolia for the use case that I was using.
Oh,
The Magnolia on Scala 2.13 is comparable.
I mean
on
the
hard
the red bar.
And the red bar, it's the semi-automatic. Here it's shapeless, and here, shapeless. Yeah, so shapeless, semi-automatic, Magnolia semi-automatic, and the same approach with macros. If we are, using this apples to apples comparison with, something like Show Pretty.
Mm. Okay.
So
well, there's a lot of stuff to gain. So better error messages for once.
That's another thing that I was also like comparing, but later on. But
performance, compile time performance.
Yeah, performance also, like, you can improve it also. Like, you can see that if you're using automatic derivation on Scala 3, then the performance could get really, really bad. So if you have automatic derivation on Scala 2.12 and migrate it to Scala 3, I encourage you to do some benchmarks.
Okay.
But yeah, also the approach with this recursive derivation instead of single macro let us have some errors, like for nested types as opposed to only the top level type. And also, if you are deriving everything in a single macro and you have all of the domain knowledge, what you're doing, what you need to do, you can also provide something like a log inside a macro that could be previewable inside your IDE. So
nice.
This is also. So this is nice because you can like easily, like if you are writing macro, this is very easy to do. And if you are doing, I don't know, whatever other approach, you can really provide your user with, okay, this is the log, how we were trying to get you the implementation. Then you can also like do all sort of stuff, like, I don't know, measuring the time of the derivation, printing the result tree, whatever. So those are the things that we are doing in Chimney. So there is a lot of stuff you can do to improve the user experience if you are writing macro. That are very hard to do, or maybe not impossible, but very hard to do if you're trying to do shapeless or mirrors or whatever.
Yeah, it makes sense actually, because it's just a program. You're writing a program. The problem is that if you are leveraging compiler-based APIs, you are limited to what they expose. But if you are using macro, you can do whatever, but you have to handle everything on your own.
Exactly. So as far as I care, probably at some point we just need a better macro standard library so that people could just combine things together with some high-level API.
Higher-level API,
High-level API to macros, so that all you have to get the stuff, start to using these things, and then get the result. And maybe then people will no longer, be so afraid of macros. Like, I know that there are some nasty part on the macros, so you don't want to write the the reflection part yourself. But I can assure you that if someone else does it for you, you will be really, really happy. But yeah.
Yeah. Okay, that was all very enlightening and exciting. I just hope that we can actually get to a point where we have some successor library that would, be like a Magnolia 0.2, because it is kind of similar. We still would need to get to a place where a user has only to, provide some small bits that the framework is going to use to actually compile everything together, glue everything together, and just build everything for you with those very fast macros. Okay, I think we can wrap everything up. We do have some questions actually. That one is not really related, but I think you are a right person to ask. So Roman is asking whether it's easy to migrate from shapeless to shapeless 3. And this is a trick question, actually. What do you think, Mateusz?
So for my very few looks at shapeless 3, I didn't investigate it much. I believe that if you only were using generic, hlist, and coproduct, and maybe witness, then migration from shapeless to Scala 3 is about removing shapeless from your library dependencies, and that's it.
Really? I mean, don't you have to rewrite your code? Because You have to replace that with mirrors.
Yeah, you have to replace
it
that with mirrors, but yeah, so you have to rewrite this code. Well, the whole code could be like written yourself, but like whenever you were doing like, but here are converting between generic representation and case class. Here I am handling empty lists of fields. Here I am appending new field to the list of fields. On Scala 3, usually you would replace it with something like bunch of sum on all when you would be mapping the tuple of types into a couple of values and etc.
So the answer, I think, Roman, is that there is no way to migrate to shapeless 3 in most cases. Shapeless 3 is...
no automatic way. You have to do this manually, case by case.
It is basically, in most cases, it is probably a rewrite of the code that was using shapeless.
Mm-hmm.
The question in context of this episode is actually whether it is a good idea to do that, because maybe it isn't. Maybe the correct way is to invest and learn how to do the sanely automatic approach. I don't think we have Pierre. Are there any tips or resources for becoming a macro expert like you?
I don't think there are yet many like written resources. I know that I think Rocket JVM was having some introduction to macros, but I don't think it's like super. It doesn't cover all of these cases like super deep, at least yet. I know that there was like streamings by Kit Langton, and he was also showing, for instance, how to write a very, very simple Chimney and implement it with macros on Scala 3. So he also was having some really, really good points. I, at one conference, The Art of Scala, I think a year ago, had like an hour-long presentation showing some differences between macros on Scala 2 and Scala 3. So there is a repository on my GitHub account when I have something like 7, 8, 9, something like that, examples showing how to implement this stuff on Scala 2 and how to implement this stuff on Scala 3. So there's like comparison between macros and some examples. And also, I can recommend taking a look at Chimney macro commons, because some of those stuff like, I have a type, is it a sealed trait? If it is, could you give me a list of those subtypes? Or I have a case class, could you give me a list of the fields it has inside, or maybe even something like a constructor?
Mm-hmm.
Then I also like implement a lot of those stuff in like Scala agnostic way or macro agnostic way. So we have an interface and implementation for Scala 2, implementation for Scala 3 handled as a mixer. So probably you could take a look and get some ideas how certain things are or could be obtained through looking at this. But they are maybe kind of complex, because I try to handle like every single corner case to make the API as bulletproof as possible, but still.
Sure. Okay, I think we have one more question from Twitch by Ola We Them Boys. Okay. And the question is, do you think Scala is dying or dead language? That's a good question. Watch what you're going to say.
I would say it's not yet dead, and depending on what we are gonna do, it's gonna die or thrive. So
yeah, I would agree with that sentiment. Actually, a lot of that depends on what we do. So
yeah, like one of the reasons I did this talk is I know that typeless derivation is awesome, but right now it's awesome if you're much into category theory and into library development. If you're a user, it's gonna suck, and we don't want our libraries to suck if we want to keep people coming rather than people leaving.
Yeah, I agree. That's a good direction to improve one of the most crucial, I would say, points of modern Scala development. We moved off from runtime reflection. We moved towards compile time reflection. It's the state of the art. That's what we are doing for a lot of stuff. It can be leveraged in many, many contexts. So, encoding, decoding, transcoding, everything that does something with data and needs to know the structure of this data, type classes are the way to go. So it's a good step, to improve the usability and how users will see errors. I fully agree with that. I will just respond in the comment, okay, Roman? That's off topic. Okay, thank you all for joining us today. And thank you, Mateusz, for joining and sharing all your knowledge with us.
You're
And
welcome.
goodbye.
It was a pleasure.
Cheers, bye.